a modern means of heating up food. But what's the basic principle behind the operation of this oven? Essentially, it radiates a wide band of microwaves which excite water molecules wherever they occur, whether they're present as the moisture content in food or just as plain water in a cup. Irradiate the water molecules for long enough and the overall temperature will rise and the water will eventually boil. It's technically simpler to use a broad range of microwaves to excite the water molecules, but microwave ovens could be tuned to radiate at very specific microwave frequencies. There are 3 frequencies that would do the job well, and as you'll be seeing, this is because water molecules have 3 normal modes of vibration, each with its own characteristic frequency, and each can cause the molecule to resonate. This is very much an idealized picture of water molecules vibrating. We'll be returning to this system later on, but first let's focus on some simpler oscillating systems. This experimental apparatus involves a smooth and level tabletop, some springs, and 1 or more cylindrical masses. One end of each spring can be secured to a side of the table and the other end to a cylinder. In fact, each cylinder contains an internal motor, which forces air out through an opening at its base. It becomes what's known as an air puck, which, very much like a hovercraft, floats on a cushion of air, almost free of friction with the surface. The single air puck adopts this equilibrium position, but how will it behave if it's displaced along the line of the springs? Well, this positioning bar is placed on the centre line of the springs, and a side spoke gives the puck an initial displacement away from equilibrium. Remove the positioning bar, and the motion you get is the simple harmonic motion you saw in Unit 7. We have only allowed the system 1 degree of freedom, since the puck has to travel along the line formed by the springs. Alternatively, you can displace the puck from its equilibrium position along a line at right angles to the original line of the springs, using a sidearm from the positioning bar, and release. Once again, you get an oscillating system which moves in simple harmonic motion. Tracing out the oscillations shows you the sine curve that's generated each time. In each of those cases, the puck moves in only 1 dimension, and the motion is simple harmonic. So actually, this system has 2 degrees of freedom, and if you release it from another point, you get rather irregular behaviour. The trace you get is called a Lissajous figure. It comes from the system having 2 degrees of freedom. The puck moves in loops, almost returning to the starting point, but not quite. It's not periodic and doesn't repeat at all. If you could overcome damping sufficiently to be able to draw the trace for longer, it would completely cover the entire area, limited only by the reach of the springs. This motion is more complicated than you saw previously, and you'll be studying this sort of motion further in the unit.